Saya sudah start streaming. Tes. Oke. Eh, harusnya dia keluar sebentar lagi. Oke, good. Sudah keluar di sana. Ya, nanti teman-teman kalau misalkan nggak bisa masuk, ada keperluan, monggo silakan. Nanti kita akan coba ini ya. Apa namanya? eh, lihat di streamingnya. Okay, so today I will talk about the meta-heuristic search, especially with genetic algorithm. Yeah, it's still the continuation of our previous material. Oke, okay, kalau ke belakang tinggalin aja, nggak apa-apa, Mas. Ya, yeah. Oke. Okay, we will continue our searching algorithm. However, we have different situation in here. In the previous methodology of searching algorithm, even though it's a blind search or it is an informed search, uh, what we do is, to be honest, the solution coming from the initial state until the goal state in the form of path finding. Okay, for example, like when we say that uh, something like the 8 puzzle. So the solution will be the step-by-step operations to what is it? To solve the puzzle coming from the initial state until the goal state. If we talk about the map, then the path from the current position into our goal position. Yeah. However, in this talk, we won't search. Our searching mechanism will be different. Okay, we already defined this one, and now we'll talk about the furniture computation. So our goal on the previous method uh, will be represented as a root. Okay, root of what? Root of the operations. So when we operate one operator coming from a state, we will change those state into another state. Okay. However, there are some problems which the the path itself is not important. The sequence of operation is not important. Okay, so the main thing is we need to know a state, which is the final state, represented as our our solutions. Therefore, in this case, to be honest, the goal state is not uh, we don't know the goal state before. Okay, so jadi yang dalam apa namanya kasus sebelumnya itu yang dipentingkan adalah urut-urutan operasi ya. Terus kemudian yang di kasus sekarang itu adalah yang dipentingkan adalah state-nya atau keadaannya gitu. Kita tidak peduli dengan urut-urutan langkah bagaimana cara menyelesaikan permasalahan itu atau operasi-operasi apa saja yang akan dioperasikan, tapi yang utama adalah the state itself. Okay, so in the previous state, in the previous case, we need to know about the goal state. However, in this problem, we don't really need to know about the goal state. Okay, uh, ada banyak yang bisa diselesaikan. For example, like in the 8 puzzle, well, to be honest, we know the goal state in the beginning before the algorithm before we run the algorithm. Okay, so this is not the case. Okay, so our case uh, is something like this. When we ask a function, for example, like we have a function of x1 to the power of 2 plus x2 to the power of 2, and then we would like to know which values of x1 and x2 will return the minimum values of the following function. Okay, so to solve this problem, we don't need an operator or a sequence of operators to solve this thing. Okay, what we need to know is only how many values in x1 and how many values of the x2. Jadi dalam kasus ini yang kita inginkan adalah goal state-nya ditemukan, bukan urut-urutan langkah bagaimana menyelesaikan X1 dan X2 sehingga ketemu sesuatu. There are a lot of problem which similarly to this case. For example, like can you cut me with can you cut when you give a paper and then there are several shapes to be cut with using those papers, then the solution is at least you will have the pattern to be cut, and then you have the result. That's itu yang diinginkan adalah hasil akhirnya, not the operation how to cut. Okay, this pattern first, and then that pattern after that pattern, not something like that. But the final result will be a matter. Okay, so in this problem, what we deals with is the h values itself. Well, yes, we can solve this one dengan pendekatan matematik with mathematic formulation. For example, like the first derivative is equal to 0. We will have 2x1. When we derive into x1, and we will have 2x1. When we derive to x2, we will have 2x2. Okay, when the first derivative is equal to 0, then that's the big values of it. Okay, in our case, that's will be represented as the minimum values of h in there. And what we got is 2x1 is equal to 0, then x1 is equal to 0, and then the 2x2 is equal to 0, and then what we got is x2 is equal to 0. That will return the minimum values of the the function of x1 comma x2. Okay, so that's how to solve the problem using the mathematic approach. However, when we ask a function, a more complex function, something like this one, well, we will face a big problem. Okay, let's say we use the first derivative. I think the derivation of this function is quite not easy. It's not really easy. I will give up to find that one using the first derivation. Okay. However, there are some approach which we can use to solve this problem. We can use using the meta heuristic, for example, like using the simulated annealing. Okay, that's a kind of algorithm that we start coming from a random position, to be honest, and then we will iterate using several direction. Okay, using several direction, and then we will find something probably not the most bukan yang terendah, not the lowest one, not the lowest one, but we can provide that the acceptance accept with some threshold, we will find some accepted values that's close to the minimum operations. And then we can also use some method like the evolutionary computation, which will generate a couple of point in there, and then iteratively this point will travel using some exploration mechanism as well as the exploitation mechanism to find different areas, and then we will compare from one iteration to another iterations, which one return the best solution for this function. Another illustrations, for example, like the traveling salesperson problem with 100 locations. Let's say we have a courier to send a package in a city which has around 8 hours working time. Well, we can give him 100 order, and yes, they have an intuition how to deliver the whole list. And for example, in these illustrations, perhaps the person who sent the packages need around 11 hours. So our company need to pay an overtime around 3 hours. Then yeah, it's spending money a lot. And then we can run another algorithm, for example, like using the Dijkstra algorithm, and perhaps we can get around 7 hours for example for 2 hours running. So before the courier start to send the packages, we need to run first, and then the courier will be what is it doing something different. Okay, and the resulted route in there is around 7 hours. Then the total time that we need to spend to that career is around 9 hours, and we need to pay around an hour overworking there. And using some other algorithm, perhaps we can run using the genetic algorithm. It's less than the Dijkstra algorithm. The characteristic of Dijkstra algorithm will always produce the optimum solution in there. However, if we solve using some technique such as a genetic algorithm, perhaps the solution is not the optimum one. However, if we run using several iterations and it produce this solution, and when we calculate these things, and we will increase our productivity. Yeah, this is the illustration, and perhaps the solution is not, or the illustration is not close enough to the real world situation. However, this it's still something that useful to study in our lectures in here. Okay, so there are a couple of optimization algorithm in term of the evolutionary computation, or there are also a couple of branches, for example, like the evolutionary algorithm, the harmonic search, and so on. And today we will learn something more specifically on the genetic algorithm. So what is this differences between the deterministic and the probabilistic one? In the previous algorithm, we can classify our previous algorithm, whether it is the blind search or the informed search, into something deterministic. Okay, why? Because when we run those algorithms using the same data, it will result uh, the same solution. Okay, why? That we have a deterministic process in there. There is no random process in our algorithm. For example, like uh, using breadth first, then we will iterate through each level. Using depth first, we will iterate something deeper, deeper, and deeper. Using A star mechanism, we will look the heuristic as well as the actual cause to be considered as our next state to be valid. And using the same data, we will find the same the same solution each time we run those algorithms. However, when we run the probabilistic one, there are a lot of uncertainty in the process. However, the process itself is quite good in terms of close to the optimal solutions. Okay, and there are a couple of approach in there. For example, like the swarm intelligence. I think for the next one, I will give you my first task is talking about the swarm intelligence. So in the next one, you can please create a slide mentioning the particle swarm optimization, explaining the particle swarm optimization, or create a slide, explain the uncolony optimizations. Okay, so you may select whether will deals with particle swarm optimization or with the uncolony optimization. So that's my first task. You may submit your slide via LMS. I will open starting from tomorrow, and then it will close around 1 week from now. So it will be around 22 of March. Okay, so make a slide explaining the particle swarm or the uncolony optimization. Okay, and make sure that you submit your slide before the deadline. Before the deadline, yeah. So today we will talk about the genetic algorithm. Okay, so the we in here we say that it's something like a black word in there, uh, something magically true. Okay, so as an illustration of our things, well, we say that the why we call those method is something classified as the black word or something not quite algorithm itself is because all of those algorithms uh, involve a lot of random process. Okay, involve many random process. Okay, meanwhile many algorithm we will say that the algorithm should be certain. That's why this kind of algorithm is considered to be something not good, but the solution itself is quite good. So even though it is a random, there are some theories behind it. For example, like this is the illustrations why the randomness is something acceptable. Okay, for example, like we have a case, yeah, if we know that the diameter is around 10 units, whether it is centimeters or meters or kilometers. So when we ask about how large the circle is, then we can have an approach using the PR to the power of 2, uh, and we have the result is 22 divided by 7 multiplied by 5 to the power of 2 in there, and we have the result is equal to 78,57. Okay, so this is mathematically correct, and yeah, there are a lot of proof that mention that this formula is used to find the area of a circle. Okay, so in the randomness approach, we can say that for example, like okay, to know the how large the circle is, well, we can give a boundary in there, and then put around 20 samples. Okay, around 20 samples, and randomly distribute in there. For example, like we will have this random position, put 20 dots in there, this one the first until the 20th dot, and then we will calculate how many right in there, divide by the whole samples that we observe. Okay, since we have oh sorry, not 20 but 16. So we have around there are 12 dots hit to the red circle, and then compared to our whole uh, whole number of points in there divided by 16, and then multiplied by the area of our rectangle. This is since it's randomly chosen from 10 to 10, then we can multiply to the area of our rectangles. So it mentioned that 75. However, it's a kind like an approximations, and it's already close to our solutions. Okay, so yeah, it is an approximation. However, if you want to be more accurate, then you can add the number of population in here, the number of samples that we have. For example, like we have 1,000 or maybe around 10,000, it will be more accurate rather than using 16 samples. And then this one, how about this one? How many areas are yang diarsir with warna merah? Okay. Well, again, using the mathematic formulations, we can say that, okay, we have the area of cycle and then minus width. We have around 1, 2, 3, 4, 5, 6, 12, 12 triangle in there, and also 12 triangles in there. So it's around 24 rectangles, and minus with this one. Okay, so well, it's quite difficult for us, even though there are still uh, we can observe those things using some mathematic formulations. However, if we use some randomness, we can, well, just put some random dot in there, and then count how many numbers which is hit to the red areas, divided by the number of samples that we use in there. For example, like there are 12 dots which is hit to the red areas, divided by 20, which is our number of samples, multiplied by the luas of our rectangle in here, 10 multiplied by 10. So we can say that the what do we call it as luas in English? I never use the word luas. How many wide? Okay. Yeah. How large the red area is? So we can say that the red area is approximately around 60 uh, unit large. Okay. So if we want to be more accurate, then we can use more samples in there. So we can put 1,000 or perhaps 100,000 numbers, and we will say that yes, our solution will be more accurate rather than the previous solutions. And if our case is something like this, well, using mathematic formulations, it's better for me to find another job to solve this job. Okay. However, if we would like to use something randomness, using involving the randomness function, we can, well, sample these things, and we will find that, okay, the red area is approximately around 80 large, 80 units large. Okay, so yeah, using something, some randomness, perhaps it's not quite accurate. However, it solves our problem. Okay, it solves our problem. It's and the solution itself is close to the optimal solutions. Okay, using this kind of approach or technique, we can continue to our algorithm in here, even though this such techniques using many randomness application or randomness process in each algorithm, we can say that yeah, perhaps it will provide some good solution, at least close to the optimum solutions. Okay, so today we will talk about the evolutionary computation. It's, to be honest, is an abstraction from the biological evolution that is used to optimization procedures. Okay, so our problem is something to find the optimum solutions. The optimum solution in here can be maximizing something or minimizing something. It's depend on our problem itself. So we take a look on the evolutionary theory. There are an idea which is mentioned that the evolution itself contain at least two processes. The first is the natural selections, which is something like quite natural. For example, like one individual, one species can become a food from different species. Using that kind of fact that we can say that in our generations, coming from one generation to another generations, there are natural selections which select which individual can be live and continue to the next generations. Okay, there are some natural selection, even though it's not the food from meskipun bukan makanan dari from one species to another species, the natural selection also happen. For example, like yeah, there are some tanaman plants which diinjak by several animals, and then those tanaman will be died, and it's not even have a chance to what is it to be evolved uh, untuk berevolusi to the next generations. And then the next concept from the evolutionary theory is the mutation. So from one generation to the other generation, there will be a mutations. Okay, even though the mutation is not always happen from one generation to another generation, however, those possibility is perhaps happen in the real world. Okay, this is the example of the evolutionary uh, paradigm. Yes, we have the natural selections in there. These pictures mentioning about the natural selections. However, perhaps some concept on the evolutionary theory about the mutation itself, it's still questionable whether it is correct or not correct. There are a couple of misproof mentioning that the previous generation of human is coming from something quite similar to the apes in there. And well, in the previous explanation, we found that there are fake fossils, and even though it is correct, why still there are monkey or apes in these days? And yeah, there are a couple of proof which mention that perhaps it's still something questionable. Even though perhaps I'm the one that quite not questioning about this thing, since we are not the biologists, we are the informatic or the computational science in here. So the concept of evolutionary theory, we can adopt that things to create something something to be useful. Yeah, this is some question about the mutations. Normally, the mutation is become something really bad, and it's not quite good for individuals. Okay, so yeah, why there is a reason in there. The DNA structure is very complicated. Uh, one randomness mutations can go to the very different thing, and it's perhaps going to something unbeneficial for the generation itself. However, today we will talk about the mechanism or apa uh, the illustration of the evolutionary algorithm. Normally, the evolutionary algorithm will have the following mechanisms. Okay, in the first is we have our initialization of the parameters that we use to the evolutionary algorithm, as well as the initialization of our initial populations. And then coming from these populations, borrowing the concept of the evolutionary theory, there is parents who married to another parents, and not all parents are married to something to another individuals. Not always an individual will be married to different individuals. Therefore, we have a kind like selection mechanism in here. And then coming from this selection, we will have a set of parent, and then with those set of parent, when the father and the mother marriage, we will recombine the what we call it sifat dari the characteristic of the father combined with the characteristic of a mother, combined with the characteristic of our mother, and then sometimes we we face with mutation conditions. So after that, it will produce a child, a couple of child, and then using some survivor selections, we will generate a new population in there. We will iterate these things many times, and then when we say that okay, our current solution is enough, then we can terminate the evolutionary algorithm. So this is the general scheme for the evolutionary algorithm, and there are a couple of evolutionary algorithm that we can learn. There are genetic algorithm, evolutionary strategies, and so on. I do apologize, I didn't know about the whole things, but today we will talk only on the genetic algorithm. Okay, so before we go forward to the genetic algorithm, we need to know about the terminology of our DNA, which we borrowed in the biological term. So there are terminology we call as a genome. Okay, so the genome is a set of chromosomes. Okay, so we say that in our terminology, the chromosome should be represent to the solution in our terminology. Okay, so what is genome? Genome is a set of chromosome, and then there are a chromosome which is a sequence of a gene. Okay, so one cell in here represent a gene. Okay, meanwhile, there are also a terminology, we will call it as a genotype, which is a collection of gene which is closely located from one location to another location, which is close enough, and a group of those genes, we will call it as a genotype. Okay, uh, using this terminology, then we can use it into our representation of genetic algorithm or the evolutionary algorithm. For example, like we will have this chromosome. Okay, let's say that this one is a chromosome representing the X1 as well as the X2 in there. When we sequence our gene 0111, 0101, we will say that the white collection of gene in here is a genotype for a something, some values, for example, like the X1. Meanwhile, for the gray collection in here represent the genotype for the X2. Similarly to the biological uh, field, each genotype, to be honest, will be represent a phenotype. For example, like our dark skin, our nose, the shape of our eyes. It's coded by this a set of gene or one genotype there. So when we have this genotype, we can say that our phenotype is the values of what we uh, encode into this thing. So this one is the sorry, what we decode into our represent genetical operation into the chromosome representations. Okay, so we have one genotype. It represents something. We have one genotype, it represents something. We have a DNA, TCG, and so on. That's a sequence of genotype, and it's represent a phenotype, which is a dark, a black hair or white hair or something like that. Okay, so that's the representation of an individual using a binary. However, we can also represent an individual in the genetic algorithm not using binary values. We can change into something different. Okay, uh, take a concern that we have gene in here, we have a genotype, we have a chromosome which built from a set of genotype. And then there are also a conversion from our previous values into a real number or using some different kind of conversions. Using this the following formula, we have the X is the our phenotype. Uh, the X is our phenotype, and then the RB in here is the lower bound, if I'm not mistaken, the lower bound values uh, of our phenotype, and then the RA in here is the upper bound values for our genotype. There will be a what is it an example if in the next slide, so don't worry if you don't quite understand in this step. Okay, so and then followed by this thing, when we have our binary representations, we can convert those binary representation into our phenotypes. Okay, and then we can also have something different, not binary. However, in here is kind of like an integer values coming from 1 to 0 using the 10th basis in there. Uh, the, we can also use different representations using the values to be converted into our our genotype into our phenotype in here. So this is the example of the previous formula. Let's say that our range of its variables which is represented by our phenotypes, is coming from -1 to 2. Okay, so the minimum number is -1, meanwhile for the maximum values is equal to 2. Okay, not this one. Therefore, when we have the binary number is equal to 0, 0, 0, since this is our minimum combinations, minimum values combinations that can be represented in our genotype of X1 genotype, then these values should be we should be converted into the minimum values in our range. Meanwhile, for the second genotype, 1, 1, and 1, as we know that this is our maximum values using the binary representation, okay? Therefore, since it is our maximum values, we should convert this genotype into 2, which is the maximum number of our range. Okay, is there any question until this explanation, until this slide? If you have some concern, please let me know. Hello, Mas Ba. Do you have any question, Ba? Mas? Belum. Oke, okay, good. Ya, jadi representasi biner ini adalah semua values dari gene we need to represent in a binary number. If we use not the binary number, then for example like the decimal one, then the representation in here can be 1, 2, sorry, 0, 1, 2 until which number that we use. For example, like using decimal representation, we will have 9, 8, 7 or something like that. Okay. However, there are some values which is applicable to a genotype. Okay, so using that range, we will say that this one is RP, meanwhile this one is the RA. Okay, uh, using the previous formula, when we have a chromosome, something like this. Let me give you some examples so you will understand the meaning behind those formula. Okay, wait for a minute. Okay, I just created a spreadsheet in here. Okay, so okay, so if we have a genotype, something like this one, 1, 1, and 1, and 1. This is our genotype. Okay, this is our genotype. So our RB in there, since it should be converted into a range from -1 to 2. So we need to follow the following equations. Okay, so our first what we can have in here is the lowest bound. Our lowest bound is equal to -1 in here, -1, and the upper bound, our upper bound is our maximum values in our range, which is 2 in there. And then using the following formula, we will have the decoder from our gene expression in here is equal to the RB plus the following values. Okay, let's say I will put those values in here. Okay, since we have -1 and then and so on. Okay, and we will calculate this one. Okay, g1 multiplied by 2 to the power of -1. Okay, we will have the power here, power 2 comma -1. Okay, this one is power 2 to the power of -2, and then this one is 2 to the power of -3, and this one is 2 to the power of -4 in that. Okay, sorry, I will give you the the link so you can open the file and then download the file if it is necessary. uh, okay, okay, I have sent the link, uh, accessing to this spreadsheet. Okay, so using the equation in here, we have that g1 multiplied by 2 to the power of -1, g2 to the power multiplied by 2 to the power of -2, and so on. And then what we need to do is we need to multiply the values on each gen in each gene with the specific encoding representations. Okay, so we have 0 0.5, 0 0.25, 0 something in there. And then since we already have this one, we need to have we need to sum all of those multiplication into a number, and then we need to also have this one. Okay, which is the summation of not the multiplication but the power itself. Okay, so sum of g sum sum of g multiplied by 2 uh, power minus. Meanwhile, on the as the divider, we have sum of not g but 2 to the power of minus something. This is equal to uh, this one. Okay, and then since we will divide the first part with the second part. Okay, the upper part to the lower part, then we will have the division is equal to this one divided by that one. Okay, and we can change the RP and RA in there, follow that the function. So we have the decoder is equal to, the first is the RB, add with the RA is equal to that one minus RB. Okay, multiplied by sum to the power of that one divided by this one. I think we need to add something like that. Okay, So our decoder is equal to 2 when we have a range coming from -1 into 2. Okay. So if we change this value, not uh, the whole gene is equal to 1, then we can change something like how if we would like to represent something which is the minimum values. So we can change this one into 0, that one into 0, and this one into 0. Then we will have the values in there is equal to -1, which is the minimum values in our range. Okay. However, if we have something different, if this is 1, then we will have the phenotype representation is minus 0.6 and so on. If we change the values in there, it will also change the values in our decoder. Okay, is it clear enough for all of you, or you have some question to be discussed in here? If you have some questions, please uh, speak up, so I will understand in which part that you haven't understand yet. Ada pertanyaan mungkin Mas Ba? Or perhaps the question apakah bisa difahami the explanations? Mas Aulia Raihan. Halo, Mas Aulia Raihan. Okay, so Mas Aulia Raihan, tes sound. Kalau nggak bisa diketik chat mungkin. Nggak ada respon. Halo, teman-teman bisa dengar suara saya? Saya takutnya saya
Iya
putus
Pak,
koneksi.
terdengar Pak dengan jelas.
Oke, terdengar ya, Pak Ardityo. Pak Ardityo. Ada pertanyaan mungkin, Pak Ardityo? Terdengar. Oke, makasih. Ada pertanyaan, Mas Ardityo? Cahyo, Mas Cahyo atau siapa? Mas Cahyo. Belum ya, dari Mas Cahyo belum. Oke, perhatikan bahwa representasi dari gen, the genome representation can be very long. For example, like I can have 4 values. The panjang dari genome yang saya miliki adalah 4 ya. Tapi however, we can also have something different. Okay, for example, like I have another representation which is still in a binary representation. Then we have this one. This one is equal to 5. It should be something 6. And this one is 7. Okay. And yeah, still following the previous formula, we change the sum coming from A to G2. And then we will change this one coming from A to G2. Okay, and the division is like that. And if we would like to represent something the maximum values of in our range, we need to fill the whole gene with 1 1 and 1. Okay, so it will decode into 2 in there. If we would like to have the minimum values, then we will need to change its values in our genes is equal to 0. If we change the range, not mentioning the -1 into 2, for example, like coming from -255 until 255, then our lower bound, we need to change the lower bound into 255 and the upper bound into 255. Then we'll have that one. Okay, so we can change this one into the yeah, this one. if we want to change this one into 0, then oh sorry, the together in here we need to add the comma in there. Wait a minute. Wait, something happened here. We should There should be change. No? Ah, sorry, 255. Okay, so this is the maximum number. This is the lowest number. Okay, and that one something different, something in between. For example, like we change that one to something like this. Yeah. Okay. So that's the binary representations, and we can also use the something not binary representations, which is the power of um, what is it? Not coming from 0 and 1. We can use decimal representations. So the values in here uh, not only 0 or 1. We can represent something like this: 9, 9, 9, 9, 9, 9. That's the maximum values. We need to change these things, not 2. Since our base is 10, then we need to change this one into 10, this one into 10, and that one into 10, this one also into 10, that one also into 10, that one, and our last one is into 10. Yeah, okay. So this is not 2 to the power of something, but this one is 10 to the power of something. Okay, yeah, this one. So we have this some, wait, did I miss something? G minus 9 minus, hmm, wait, there's something missing here. Hmm. Oh, okay, 9 multiplied with, okay, 9 multiplied with, okay, something like this. Okay, this is represent the second formula in there. Meanwhile, for the bottom one, I think we just add the whole things. We don't represent using kind of values. This is the values, for example, like an integer values, and then we just add it in there and then multiply it into something different. Or perhaps we have some range like real numbers in there. We can also represent our chromosome using this kind of representation. Okay, so we have discussed this one. Uh, this is our range, this is our phenotype, this is our genes values, and this is our phenotype. We can convert from our genotype into the phenotype. There are usually some questions regarding to this process. Do we need to convert from our phenotype into our genotype? So the answer for this question is in our genetic algorithm, or in our evolutionary algorithm, we don't need that representations. Why? Since our process always deals with the gene expressions, we don't we never deals with the phenotype expression, except that the phenotype things represent the values to our case. We will discuss later on. However, the answer for this question is we don't need to convert from the phenotype into genotype representations. Okay. Okay, so this is another example, and we have explained this one. This one also another example explaining something differently, mentioning the third formula in the previous slide. And then we have also a permutation representation, not the binary, not the decimal, not the real number itself, but it's something, the values in there is a number which is a permutation values from the first position until the last gene that we have in our genotype. Okay. Jadi nilai-nilainya adalah nilai-nilai permutasi dari posisi gen pertama hingga posisi gen yang terakhir. Jadi dia nilai permutasi. There is no similar values between one gene to another genes, okay, in the permutation representations. When we have this kind of representations, we can formulate into this kind of problem. For example, like from this point, going to the from the first position, going to the fifth position, going to the second position, going to six, three, four, and then go back to the first position. And it's kind of like a specific formulation for the traveling salesperson problem, since in this traveling salesperson problem we need to visit its nodes at most is equal to one. It's almost similar to the courier in our previous previous what is it previous cases. Okay, Mas Andi, can you mention your question directly, please? Mas Andi.
Oke, oke, Mas Agung. Uh, Pertanyaan saya itu adalah, kan dari tadi saya lihat phenotype-nya atau datasetnya itu rata-rata number gitu ya, kumpulan number. Yang saya mau tanya, kalau misalkan datanya itu tipe data bentukan atau objeknya ada banyak, bukan cuma satu single, uh, itu gimana caranya kalau kita mau ubah ataupun menggunakan algoritma GA ini? Gitu.
Okay, thanks, Mas Andi. It's I think this question is more advanced question to the genetic algorithm or the evolutionary algorithm. There are two solutions, to be honest, Mas Andi. We can deal with something like indexed representation. I will give you an example. Wait. Let's say we deal with two objects, several objects. Okay, this is the first object. This is the second object. Okay, and then this is the third object. Okay, it's not a number, like, right, Mas Andi, and deals with this object. We say we have something different. We can have something different. For example, like this is the first operation, the first representation of the first object. Okay. Meanwhile, this one is the second representation of the first object. Okay. The second one also similar to the first one. This is the first representation. Okay. And this one is the second representation of the second object. Okay. Meanwhile, for this one, let's say that we only deals with the 90 degree of rotation. This is the first representation, and the second one is the this is the second representation of the third object. Okay, if you would like to what is it menata this object, the first, the second, and then the third into a smaller space, for example, like into this space. How can we how can we how can we arrange this object? Sorry, let me give you a different color. Can we arrange this object, the first, the second, and then the third object into this space? Okay, then there are a couple of a couple of solutions, and those solutions can be represented using the genetic algorithm. Let's say that we have two things. The first is the object itself, and then the second is the orientations. Okay, whether it is rotate 90 degree, rotate 180 degree, or rotate 270 degree. Since we have two attribute in there, the shape as well as the orientation, I think it's answer your question already, right, Mas Andi? How to deal with an attributes of of a data. So this phenotype, the first representation, to be honest, is has two genotype. Okay, the first is the shape. Okay, the shape itself. We can have one, two, and three. Okay, so it will range. The first genotype is 1,2,3. Meanwhile, for this one, we have two things, which is in the zero rotation, with a 0 degree rotation, or with a 90 degree rotations. 180 degree rotation is similar to the 0 degree, so we have only two values in there. So meanwhile, for the second genotype, we'll have two possibilities. Okay, dealing with these things, we can have binary representation, integer representation for the first genotype, binary representation or integer representation to the second genotype. Okay, since we have three object, then we will have three genotype, three pairs of genotype. That's the first, okay, that's the second, and then that's for the second object. This is for the third object. Okay, so dealing with these things, since we can put the rectangle first, the long rectangle first, and then the triangle or the combination of it, we can also have another genotype. Okay, so uh, not another genotype, but we have since we have three objects, we will have three genotype in here: the first, the second, and the third. Okay, so this one is kind of like what is it? Permutation representation for the sequence of object to be put in this blank space. For example, like in the paper or in the plate or something like that. Uh, this is the sequence of object. and then this one is for the second object. This is the representation for the third object. That's the first representation, Mas Andi. So we can use with something like this. And then the other thing is, if we don't want to represent using this kind of things, we can have a decoder in here. This is our first object. This is our second object. This is our third object. This is our fourth object. This is our fifth object. Or we will have we have a list. We maintain a database for each solution in there, and then using for this kind of combinations, then we will have a kind of like representations. Okay, we have 1 until 6, and then we have a binary representation or something like that. I hope it's answer your question, Mas Andi, or if you have some discussion, please go ahead.
Oh, oke, udah kejawab, Mas. Jadi tinggal direpresentasikan ke bentuk yang lain gitu ya.
Yes, we need an imagination, to be honest. Yeah. Okay. Okay. Is there any other question? Please, if you have some question before we go to the genetic algorithm itself, go ahead if you have some question. Fellows? No? No question? Okay. I think we already talked a lot, and I hope we have a break after I continue to my explanations. Therefore, I think I need around 10-minute break. Is it okay, Mas, Mbak? If
Oke,
it is
Mas.
okay, then we will meet again at 16 54. Okay, thank you very much.
Mas,
Yes, Mas Nur. Sorry.
untuk link YouTube pertemuan pertama dan kedua belum di-share, Mas.
Oh ya, saya belum sempat mengirimkan karena kemarin saya record di sini. Nanti akan saya upload. Makasih banyak, Mas.
Oke, siap. Makasih, Mas.
Okay, thank you very much.
Naka's Botez Gambit speedrun. The truth hurts. Botez Gambit speedrun be like, yeah, it's like Usain Bolt laughing at the other competitors or smiling. A 2300 trying not to lose. Naka down a queen and speaking to chat. Exactly. Yeah, this is a good one. First one. Of course her name is Karen. Karen, last seen with the kids today. Do you like anyone? Yeah, you. I have a boyfriend. Yeah, you. Oh, haha, thank God. Yeah, no, I'm single and I don't have anyone I like. Okay, this is really good. That's actually really, really good. Yeah, with that look, yeah. Good one. It's about the wording. Missing a hanging queen. Botez Gambit declined. Yeah, exactly. True. All right, what's next? We have chess is a game of unlimited beauty. Day 1 of chess. Okay. Day 365 of chess. Also pretty good. Good one. Very true. Interesting. Empress Ani says, so a queen is of course a girl, right? At least in ancient times. And pawns can turn into a queen. So all pawns must be girls too. And pawn can turn into any piece except the king. That means all the pieces beside the king is a girl. So basically, chess is harem war between two sides, and then you still each harem member one by one, like NTR. This is why chess is hot. Wow, wowzers. Okay. What am I even supposed to say to that? I don't know. Evil laugh. What is this? Evil laugh. Ha ha ha. Okay. 0, 0, 0, 0, 0.
Hello, does anyone hear?
Hadir Mas.
Hadir ya. Okay, thank you, Mas. Okay, so let's continue to our talk today. The next one is the fitness. Okay, so what is the fitness? The fitness in here is the values that we would like to optimize. There are two type of fitness. The first is the maximizing something, or we need to minimizing something. Okay, when we deal with maximizing something, then we can take the values of that function as our fitness. However, if we would like to minimize something, we need to be put the function in the bottom of our division equations plus something small number representing or menghindari dari pembagian dengan nol, division with zeros in there. So for example, like our function in here is the x to the power x1 to the power of 2, and then x2 to the power of 2. Then we have something. If it is not a maximization function, it is a minimization function, then we need to add a very small number in there, just only to avoid the division with zero. Okay, to be honest, on the maximization and then the minimization something, the fitness values in there represent that the solution achieved by a point in here. We can say that its chromosome or its individual as a solution uh, is represented with the fitness values in there. So be careful with how to design with the minimization or the maximization function that we have. And then the fitness function also useful uh, to be used in the next process, which is the parent selections, or the what do we call it, offspring selection. Let me check it in the Google Translate. Offspring. What is offspring? Okay, I cannot find it in the net. It's yeah. So when we deal with parent selections, there is what is it? Rationale behind this. The chromosome with greater fitness, or with the highest fitness values. Uh, in the real world, individual with highest fitness values, for example, like we can say that the more handsome people have a more chance to be selected as a parent. The more beautiful people have a chance to be selected as a parents in there. If we say that the handsomeness or the beautifulness of an individual is a fitness function that we use in our society, then we will have a kind like a roulette wheel mechanism, which when we have the highest fitness values in there, it's represent with the wider area in the roulette wheel method. For example, like we have these combinations, the for its fitness function in there, when we accumulate on the whole fitness function, we have the 8 in there. So the first chromosome, or the first individual in there having 2 fitness function divided with 8 is approximately equal to a quarter. This is the area for the first chromosome. Meanwhile, for the second and the third is equal to 1/8. This is the second and the third. And then for the fourth one is fourth divided by 8 is approximately equal to half of the area. So a parent selection mechanism in here using the roulette wheel still maintain that even though the fitness function is an individual or a chromosome having the lowest function, the lowest values of fitness function, still there is a chance for them, for those chromosomes to be selected as a parent. So using this kind of roulette wheel, when we roll out the wheels, then there are possibility for K3 and then the second chromosome to be selected as a parent. Let's say we need to select around a fourth selection in here. So we will roll the roulette wheel and we have the K3. We will roll also for the second one. We have the K1. We will roll this one into having the K2, and then we roll the roll again, and then we have K1. So we have K3, K K1, K1, and then sorry, K1, K2, and then K3 as our parent set. And then the second thing is recombination. The recombination in here deals with in which point we need to recombine from the parents to generate the child here. For example, like we select two parents, the first parent and then the second parents, and it will be recombined using this cutting point. So we can recombine into the first one is having the first, and then the second part having the second part of the second parent. Meanwhile, for the second child, using the similar cutting point, we have coming from, let's say, the mother, and the other side is having the father's genes in there. So this is the recombinations. Consider that the roulette wheel is kind of like a random situation, as well as the recombination here is also a random process as well. How to define the cutting point in here? We can have cutting point in there, or the cutting point is in here. So the position in there is determined in within random operations. And then for the mutation itself, when we have a child in here, okay, we can say that if the mutation exists, so we can randomize the gene to be mutated or changed into some values. For example, like if this gene is mutated into different values, then we just change the values in there into something different. If we use the decimal representation, so we deal with the position of an index, we can change into something different. For example, like from 0 into 9 or from 0 into 5 using some random mechanism. Therefore, for the mutation itself, this is the initial condition before mutation, and this one is the condition after the mutations. And then we have this one is the child chromosomes in there. So previously we have populations using our iterations. We need to select some parents using the roulette wheel. We have uh, a set of parents, and then we can mate. We put the parent into some mating pool. We can mate the first parent with the other parents to have a child, and then after we recombine and then mutate some gene in its new child, we will have an N chromosome, an new chromosome. And then when we have a new population in here, we can select a couple of individual in our populations to be discarded and replaced with a new chromosome, or we can replace the whole population with a new chromosome in here. That's we will call it as a survival selection. We can have a generational when we use with the general rational, then the whole population will be replaced with the new chromosome. Meanwhile, if we use the survival selection or survival, the survival selections is using the steady state mechanism, then we need to change an M chromosomes in our populations with the best chromosome in our new our child chromosomes. For example, like we can select the worst values in there with the new one. That's the two mechanism the in the genetic algorithm, especially in the survival selection. Let's say that we do with something different. We have we want to maximize the function of the following function 7x1 minus 3x2. We can say that to maximize this thing, we need to maximize the x1 part. Meanwhile, we need also to minimize the x2 part. Okay, so when we have the range is equal to 0 and 15, so we have the maximum values is for the x1 will be equal to 15. Meanwhile, for the x2, since we would like to minimize the penalty in there, we will select the 0 in there. How to have this solution in using the genetic algorithm? Okay, this is the maximum values obtained that using the following formula. Let's say we use the binary encoding in there. The representation of the x1 and x2 is equal to 3. X1 is equal to 5 and x2 is equal to 3 can be represented into this binary encoding. Okay, even though in the previous question, in the previous discussion, I mentioned that we don't need this process. Okay, we can skip this process, and then the chromosome itself is initialized with random values. For example, like, okay, this is the first chromosome. I will random the values on the first gene, the second one, the third, until the last gene values in there. The whole thing in the genetic algorithm can be done with a random process. When I random the values in there, it can be represented into some phenotype values using the previous one. And then since our case is the maximization operations, we will take the values of our function as the fitness function in there. Therefore, we have this one. We will change K1 into the phenotype, the second part into the X2 phenotype, the second chromosome, the first genotype into the X1, and then the second part into the X2, and so on until the fourth chromosome in there. Therefore, when we have this chromosome, we will have the individual representation for the phenotype is equal to this thing. We have discussed this before, and then we can change this phenotype into a fitness function using the following formulas, and then we can accumulate the whole fitness function, and then we will change into some probability in our roulette wheel. Okay, and then we can roll the roulette wheel. For example, like in here, since it's approximately dominant, when we would like to select around 4 parents in there, so it should be selected around 2, and then it should be selected around 1, it should be selected around 1. Meanwhile, this one, it should be selected around 0. It's close to 0. However, in the actual mating pool, the different situation can be happen since we need to roll the roulette wheel in there. let's say that the first chromosome is selected twice, the second one is selected only one, and then the third one is selected only one. Meanwhile, for the last chromosome, we are not selected in the mating pool as the candidate parents there. So this is the our mating pool, the K1, K2, K3, and sorry, this is our mating pool, K1, K3, K1, and K2, and then yeah, this is the parent selection. And then what we need to do is recombine the first couple, and then the second couple we need to recombine as well. And then for example, like this is the first couple, we put that position become our cutting point, and that position become the cutting point for the second couple. And then we will have this recombination for the first, and then this is the recombination for the second. Okay, using this one as our child recombinations, we can have a mutation. Okay, the mutation can be applied to each chromosome in here. For example, like in this process, we have a situation when there is no mutation applicable to this chromosome. Then we will have the phenotype for the first child, the phenotype for the second child until the last one, and then we can change. We can have the fitness values for each child in there. And then if we use the generational replacement, then we will change the whole generation, the whole chromosome in the second generation into the one that we have in here. Okay, so this is become the first chromosome. It should be the second chromosome. Oh no, not that one. Um, this is the recommendations. There must be something different in here. Yeah, but the thing can be happen if we use the generational replacement. The whole population will be replaced with what we got in here. However, I think in the next slide, it's not the generational replacement. It's kind of like a steady state replacement, I think. Yeah. So if we use the generational replacement, we have this one as our population. We have 105. This is the maximized, the optimum solution. And to be honest, in the genetic algorithm, we need to maintain the best solution so far. Therefore, if we use the generational replacement, the best solution will be not replaced with the other solutions. Okay, that's the illustration for the genetic algorithm. If you have some questions, please go ahead so we can continue to the next one. Any question, Mas Mbak? Not yet? Hello? Oke, kalau belum, mungkin kasus berikutnya adalah minimasi. Jadi contoh misalkan minimasi yang tadi, kita berada pada range minus 5,12 hingga 5,12 ya, dari minus sampai positive values. Kalau di posisi itu mungkin kita akan menemukan bahwa nilai maksimumnya ada di keduanya adalah 5,12 ya. Sorry, minimum values-nya adalah di posisi 0,0 ya, 0,0. Jadi kita bisa dapatkan, katakanlah ini adalah individu yang pertama, representasinya kita bisa gunakan sepanjang apapun ya, seperti yang tadi sudah kita utarakan. Kita bisa gunakan yang ini adalah G1 ataupun kebalikannya ini adalah G1, seperti itu pun bisa. Terus kemudian karena ini minimasi, maka fungsi fitness kita adalah 1 per dari nilai H ya, ditambah dengan 1 bilangan kecil. Bilangan kecilnya bisa lebih kecil dari ini. tergantung dari teman mana yang preferensi dari teman-teman ya. Oke, so ini nilai katakanlah kita menggunakan 50 kromosom dalam satu populasi, maka kita harus generate ada 50 kromosom ya. Masing-masing kromosom sebagai salah satu solusi ya. Kita punya ada phenotype apa namanya konversi dari individu ini ke phenotype masing-masing. Terus kemudian dihitung nilai fitnessnya, terus kemudian dari sini nanti kita akan punya apa namanya akumulasi dari nilai fitness ya. Akumulasi nilai fitness itu menunjukkan area dari roulette wheel sehingga nanti pada saat kita putar roulette wheel akan terpilih parent-parent yang ada seperti itu. Dengan genetic algorithm katakanlah pertama kali poin-poinnya diposisikan dalam posisi random, ternyata dalam generasi yang berikutnya dia mampu untuk mendapatkan nilai yang lumayan bagus. Di sini nilainya sudah mulai naik dalam beberapa kasus ya, seperti itu. Dengan ilustrasinya mungkin ada beberapa poin yang sudah berada di puncak, terus kemudian ada semakin generasinya kita lanjutkan mungkin yang di sini menggunakan state kalau tidak salah ilustrasinya. Jadi poin-poinnya mencapai pada posisi yang lumayan bagus ya di sana seperti itu. Itu mungkin yang bisa disampaikan terkait dengan genetic algorithm. Jadi kalau seandainya nanti teman-teman gunakan genetic algorithm, mungkin kalau dari mekanisme yang tadi, maaf saya kembali ke representasi ini. Oh sorry. So in the genetic algorithm, we have no, not that one. Okay. So in the evolutionary algorithm, the framework in here we will have a loop. Okay, loop ini bisa terjadi berkali-kali, gitu ya. Semakin panjang loopnya, tentunya waktu yang kita butuhkan semakin panjang. Dan tentunya ada proses terminasi kalau kita berjalan terus-menerus, maka tidak mungkin kita akan berhenti gitu ya. Terminasinya bisa beragam, contoh misalkan tadi dalam ilustrasi kita bisa hentikan dalam waktu ya. Let's say we only have around 10 minutes or 20 minutes, then we will run our genetic algorithm using specific time. Or we can also have the termination criteria is how many generation that we will apply to our evolutionary algorithm. So that's also applicable. The other thing is we can also set certain values or certain threshold to determine whether our solution is acceptable or not acceptable. Okay, if we mention that okay, it's already acceptable, then we can terminate our loop function in here, our loop mechanism. Okay, go back to the next slide. I think there is a discussion in here why the evolutionary algorithm is powerful. Let's say compared to the brute force, the evolutionary computation is powerful since we have a mechanism, to be honest. Even though it's a random process, however, using the mechanism in there, we can select the best individual and maintain the best individual, and perhaps in the next generation we will have a better individual compared to the previous generation, and then it's repeat in a couple of iterations, and we will provide some good solution, even though the whole process is still using the random things. There are a couple of books if you would like to read. It's Professor Sianto's book. There are two books: the genetic algorithm, as well as the evolutionary computations. So if you would like to deepening your material on this area, I will recommend to read this book, so you will understand some terminology that we haven't found in these lectures. I think that's the whole explanation for today. If you have some question, please give it to me now. If you don't have any question, then we can terminate our lectures today. Is there any question, Mas, Mbak?
Mas izin Mas.
Okay. Yes, Mas
Untuk
Andi.
yang fitness function itu apakah bentuknya selalu seperti itu atau itu kita sesuaikan dengan problematika yang ingin kita capai solusinya?
Okay, good question, Mas Andi. Okay, in this case, perhaps the fitness function is different. Okay, well, we need to. It's really hard to explain. Therefore, I will use something different, Mas Andi. Wait a minute. Oh, I think I already have it in here. But okay, this one. Okay. When I have these situations, okay, and then since our chromosome is represent the next destination for the traveler, okay, from the first position to the fifth position to the second to the something like that. Imagine that the solution or there are a couple of candidate solutions that we have. Okay, for example, like I can say that 2, 1, 3, 5, 4, 6 is solution as well. Okay, let me put it in sorry, let me put it in plot so we can discuss for further discussion. Okay, so we have these things. Okay, so this solution 2, 1, 3 okay, 2, 1, 3 can be represented by a line coming from 2 going to 1, 1 going to 3, wait a second, 1 going to 3, and then 3 going to 5, and then 5 going to 4, okay, and then 4 going to 6, and then 6 travel back to 2. Okay, as you can see that the first solution, the black solution, it's quite good compared to the red one. Okay, however, there are other solutions which is better than that one, which is when we go from 1 to 5 and then going to 6 and then going to 2 and then going to 3 and then going to 4 and then go back to 1. I think the black solution is not quite good enough compared to the blue one. Okay, so in that case, different cases will have different kind of fitness function formulations, Mas Andi. It's depend on our cases. Yeah. Is it answered your question, Mas Andi?
Saya bingungnya di formula apa Bagaimana cara kita menentukan formula?
How to define the formulations. That's
Yes.
also another challenge when we use the genetic algorithm or the evolutionary algorithm things. Okay, the evolutionary algorithm based when we apply the algorithm in there are two major challenges. The first is how to represent the chromosome. Okay, and then the second is how to deal with the fitness function. And yes, your question is correct. That's the hardest part of it. Um, I'm not able to answer that question properly, since when we face with different situations, then we will have a different formulation for the fitness function, Mas Andi. But yeah, for the maximization problem, then we will have the fitness function is equal to h, and then for the minimization function is equal to 1 divided by h plus a. The big question is how to define the h function itself. In here, since we would like to minimize the kilometer, the distance in there, then we can say that the distance between the first position to the second, added by the second to the third added by to the fourth, added by the fourth to the fifth, and so on. Okay. However, in different cases, for example, like when you would like to create a schedule, okay, there are some fitness function. For example, like we need to minimize uh, the bentrok schedules. What do we call it? Bentrok in English? Yeah, jadwal yang bentrok harus kita hindari. And then overtime schedules, for example, like a schedule from an employee which is scheduled not in the office hour. That's also we need to minimize those kind of things. Yeah, but yeah, different situations or different problem will have its own its representation, its function representations, Mas Andi.
Okay, so
Sorry, it's probably not quite answering your problem enough, but I try my best
yeah,
to answer your questions. Yeah.
yeah, no problem.
Okay.
Thank you, Mas Agung.
Yeah, sama-sama Mas Andi. Is there any other question, Mas? But if you have some, just go ahead. Okay. Mangga Mas Andrea Malala Lauren. Mas Lauren. Please, Mas Lauren. Halo. Mas Lauren, can you speak up? Sorry, does anyone heard Mas Lauren question? Ada yang dengar suara Mas Lauren enggak?
No, sir.
Nggak ada ya. Oke.
Hmm.
Mas Lauren, is there any references in English, sir? Yes, you can search the evolutionary computation. Then there will be a bunch of references. Go to this Google Scholar. I think you already know the Google Scholar, or you can Google it. Book. There are a couple of references in there. I didn't know if our open library already have open library already have the evolutionary algorithm book, but we can try it. Evolutionary competition, evolutionary. No, this one. have the music. I think it's coming from your side. I think you can download this one. Yeah, just download this PDF, and then you can read a lot the theory behind it. Yeah, Mas Loren.
All right. Thank you, sir.
Yeah, you are very welcome, Mas Loren. Is there any other question, please? If you have some question, is it enough? Okay. Since you don't have any other question, and we also didn't have any other materials, the other materials I provided in term of a task, which is please create a slide explaining the uncolony algorithm or the particle swarm optimization. Basically, you can uh, read many articles in the internet talking about those two algorithms, and then create a slide of it, and then please put it in the our LMS. I will open it tomorrow, and then our deadline schedule is around 22 of March. Um, in 8 p.m. Indonesian time or Jakarta time. Okay. Okay. Thank you very much for your attention, and goodbye everyone. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam. Terima kasih.
Terima kasih.